Good afternoon, everybody, and welcome to this webinar for the AI for RealNet project about distributed and hierarchical reinforcement learning. This is the outline of our webinar. So we will start with an introduction in which I will provide a general overview of the AI for RealNet connection with the distributed and hierarchical reinforcement learning frameworks. Then I will leave the floor to Gianvito and Marco, who will go deeper into the presentation of the distributed and hierarchical frameworks. And finally, I will wrap up by providing more concrete research direction that we are currently investigating and we are planning to investigate in the context of the project. So why do we care about distributed and hierarchical reinforcement learning in the AI for RealNet project? Mainly because those are frameworks that are helpful for addressing some of the main challenges of the use cases that have been defined in the context of the project. Specifically, the complexities of this use case can be, say, identified into two categories that are the curse of dimensionality and the curse of horizon. For what concerns the curse of dimensionality, this is related to the fact that the decision process underlying is characterized by being a process in which we have a large, possibly infinite state space, as well as the decision space can be very large, making this decision process very challenging. And this complexity, the curse of dimensionality, can be effectively addressed by resorting to distributed reinforcement learning. Instead, for what concerns the curse of horizon, this is related to the fact that the decision process is required to plan in the far future, so to identify a very long sequence of optimal decisions to be taken. And this, again, is another source of complexity that instead is particularly suited to be addressed by using another framework that is hierarchical reinforcement learning. More concretely, let's, for instance, consider two of the use cases of the project, the electricity use case and the railway use case, in which both of them are characterized by the fact that the decision process is decentralized across different control centers. So we are in a scenario that is naturally distributed in the sense that this intelligence is split among several centers. Moreover, there is a form of interaction between the several centers that involves the presence of higher level agents which are in charge of mediating among the decision of the single control centers in order to arrive to a final decision for the process. And so we are as well in a scenario in which there is some hierarchy involved. This is also true for the air traffic control scenario, where here the presence of multiple agents that are in charge of portion of the complex decision process is clear because the traffic space is split among several operators which interact with a higher level operator, a manager, that is in charge of mediating among the different decisions in order to arrive to the final control methodology for the system itself. So also in this case, we identify some characteristics that make the process distributed, and as well we have a hierarchy of agents which are involved in the overall decision process. So now that we have understood from a high-level perspective the fact that in the use cases of the AI for RealNet project we have distributed and hierarchical aspects, we will go deeper in these two frameworks. And now I will leave the floor to Gianvito for the distributed reinforcement learning part.
Okay, in this part, we will focus on distributed reinforcement learning, and we will provide some, we will start from the basic definition of distributed reinforcement learning and provide some intuition on the main advantages and disadvantages of this framework. So again, the main motivation is the problem that Alberto mentioned before, the curse of dimensionality. So in which we have large potentially infinite state space and action space, and we want to break the complexity of the problem by distributing the learning process. So the definition of distributed reinforcement learning is a distributed learning process to solve a sequential decision-making problem. So the emphasis here is on the fact that the learning process is distributed, and this is different from standard reinforcement learning, where the learning process is concentrated on a single agent. Here instead, we have multiple agents that are involved in the decision process. So for example, here you can see multiple robots that play in an environment. And in this case, we call this field more generally as multi-agent reinforcement learning. We will see in the following slides that distributed reinforcement learning is a special case of multi-agent reinforcement learning. Okay, an example of distributed reinforcement learning is RoboCup, which, as you can see here, is a competition in which a team of robots play soccer. So a team of robots has to learn how to play and how to win the game by leveraging on communication and coordination among the multiple players of the team. And this poses some challenges that we will define in the following slides. So first of all, starting from problem formulation, we have a mathematical framework, which is called Markov game, that can be used to model multi-agent problem. So starting from the picture here, you see on the left, we have what is called a Markov decision process, and it is the standard framework of single agent reinforcement learning, where we have a single agent that plays an action A in the environment and receives a new state S of the system and a reward signal R. On the right, we have the extension of this framework, so the Markov game, in which, as you can see, we have multiple agents from 1 to n. Each agent plays an action A from 1 to n and receives the new state of the system S and a different reward signal R from 1 to n. So a Markov game can be modeled as a tuple with a list of elements that you can see there. So n here is the number of agents. S is the set of possible states of the environment, so the state space. AI is the set of possible actions that are available to agent I, so the action space. P is the state transition function, so the dynamics of the environment that basically gives the probability of transitioning to a new state, given that the agent is in a specific state and plays an action A. Then we have RI, which is the reward function of agent I, and let me say that the reward function is a very important function in reinforcement learning because it gives an immediate feedback on the actions played by the agents. So how good are the actions of the agents? And it encodes so the general objective of the problem. So in the single agent reinforcement learning, there is a single reward function, but here we have multiple reward function, one for each agent. Then we have H, which is the horizon of the problem, so the number of interactions that the agents do with the environment, and it can be a finite number or infinite depending on the problem. Then additionally, we have pi I, which is the policy of agent I. So this is the actual behavior of the agent. So given that the agent is in a state S of the environment, pi I is the probability for the agent to select a specific action. Okay, so given that we have the mathematical framework, we want to define an optimal objective of the problem, and we need to introduce the concept of value function, which is a very important concept in reinforcement learning. So here, VI is the value function of agent I and depends on the policies pi I, so the policy of agent I, and pi minus I, which is the policy of all the other agents except I. So in this case, this is the expected sum of the rewards accumulated from time t equals 0 to the horizon h playing action AT, where each single action AT is composed by different components. So the component I is sampled according to the policy of the agent I, and all the other components minus I are played according to the policy minus I. And the starting state is S. So here it is clear to see that the performance of each agent I is controlled not only by its own policy, pi I, but also by the choices of all the other agents, pi minus I. So this makes the learning process challenging, and the most general objective of multi-agent problem is what is called Nash equilibrium, formulated by the mathematician Nash in the 50s. Nash equilibrium is a joint policy, so the set of the policies of all the agents, pi 1 to n, here denoted with star, such that for any state S and for any agent I, we have the best possible combination of all the value functions. So that means that all the agents at the same time maximize the cumulative sum of rewards. And so here, VI on the left is dependent on the policy with star of the joint policy, and that is always larger than the value function depending on the policy pi minus I of the joint policy and any policy pi I of the current agent. So Nash equilibrium is an equilibrium in the sense that all the agents want to stay in this point and don't want to leave this equilibrium. And it has been proven to exist in many problems, but in practice, it is difficult to find algorithms that converge to such equilibrium. Now we will see some paradigms of multi-agent problems. So there are in total 3. One is cooperative, in which all the agents share and optimize the same objective. So for example, the reward function of all the agents are the same, and this is called generally team game, in which the agents play as a team, and in this case they need a form of communication, so they need to share some information in order to efficiently learn the shared objective. Then we have the competitive scenario in which all the agents are in competition, and one example is zero-sum Markov games, in which the sum of the rewards of all the agents is equal to 0 for any state action pair. And that means that increasing the reward of one agent makes the reward of the other agents decrease. And one example of competitive multi-agent problem is 2-player games. For example, tic-tac-toe here, where each player wants to win the game, and so it's in competition with the other player. Another possibility is a mixed setting, which is a combination of the previous two, and an example are general sum games, in which the sum of the rewards is a general number. And here I want to specify that distributed reinforcement learning is a special case of multi-agent reinforcement learning, in the sense that it deals with cooperative problems, and we will comment more on cooperative problems now. So the first question is how to distribute the learning process. So one possibility is to have what is called centralized training. So as you can see, we have our agents from 1 to n. Each one receives some observations from the system and shares some information with the central controller. So for instance, the local policy or the observations. And so in this case, the central controller has a global view on the system and can efficiently drive the learning process of each agent. Centralized training can be coupled with centralized execution, in which also at execution time, the agents share a centralized source of information, or decentralized execution, in which agents are independent at execution time. Another possibility is to have decentralized training and execution, For example, on the right, you see that all the agents are independent, so they basically run single agents, reinforcement learning problems, and they ignore the presence of the other agents in the environment. Or alternatively, we have the situation in the middle in which there is no central controller, but agents are connected to other agents. So meaning that they have some form of communication, they share some form of information to address the learning process. Now we will see some challenges of multi-agent problems. So first of all, the fact that we have non-unique learning goals. So in the Nash equilibrium that I described before, I said that we have a combination of multiple value function, and that means that we have different learning goals, which is a challenging problem. Then we have non-stationarity, meaning that when agents do not have information about the other agents, how they, what they observe, how they play, they perceive the environment as being non-stationary. So it's like it changes behavior over time, and this typically required to collect a larger number of samples. Then we have multi-agent credit assignment, so the problem of understanding whose action among multiple agents have contributed to the rewards. And this is crucial because we want to understand which action need to be reinforced for each single agent. And this again can require the necessity to have a larger number of samples at training time. Then we have scalability. So in the case of centralized training, in which we collect all the state and action of all the agents, we incur again in the curse of dimensionality, because we have an action space and the state space that increase exponentially with the number of agents. And then we have various information structures problems. So in the case of communication, we need to have many ways of communicating information, and that needs to be synchronized with the environment and all the interaction that the agent have with the environment. Now we have briefly a look at two state-of-the-art algorithms for distributed reinforcement learning. So the first one is a distributed version of Q-learning, and Q-learning is a very popular algorithm in reinforcement learning. Here, the extension is QD-learning, which is a provably convergent algorithm in distributed setting. And here I reported the main update formula. Let's not focus on the details. I want just to show you that here, so the Q function, Qi, is an extension of the value function that we have seen before. So the expected sum of the rewards starting from state S and playing action A by the agent I. So in this case, we have the blue term, which is from the standard Q-learning update, which takes into consideration the reward of agent I plus an update depending on the Q function of the agent I. And then we have the yellow term that, as you can see, is a combination of the Q function of different agents with the index J, where J comes from a set of neighbors of the current agent. So that means that the agent communicates the Q function with a limited number of agents that is in its neighborhood. Then we have distributed PPO, where again PPO is a state-of-the-art algorithm for single agent reinforcement learning. And we have the independent version in which you can see in the picture, we have the multi-agent environment. In this case, for example, 3 agents, each having its own policy and value function and trained according to a PPO loss, as in this case, we have neural networks, basically. So in this case, we have the independent version, and then we have the version with a centralized critic. So in which agents have their own policy, but then they share the value function, which is called critic in this case. And this means that when they train their policy with the loss, they have a source of information which collect information from all the agents, so provides a centralized form of information for training their policy. Now a summary of what we have seen so far. So we have seen that MAR problems can be modeled generally as Markov games, and Nash equilibrium is a theoretical objective that is difficult to reach in practice. Then we have that distributed reinforcement learning requires a trade-off between what is independent learning, in which we saw that agents are completely independent and do not share information, and fully centralized setting in which they have a centralized mechanism. We have that almost all the state-of-the-art algorithms today focus on centralized training and decentralized execution, because it helps solving some of the main issues that we saw in the previous slide. So, for example, non-stationarity and credit assignment. Then we have that for the fully decentralized case, PPO gives the best results in general for independent learning. And one of the most important questions about multi-agent problem is how to communicate. So which kind of information needs to be shared, and how they can be communicated among the agents. Here, in this slide, we will see a map. So we have the three main categories of the algorithms that we have seen so far. So the centralized training, the centralized execution, or centralized training and execution on the left, and the centralized training execution on the right. Here, the number of dots basically gives you the idea of the number of state-of-the-art algorithms per category, and we see that most of them are on the left part, so in the centralized training setting, while only a few algorithms are in the decentralized training and execution. And this is because, again, it's difficult to find algorithms that have only limited amount of information that are shared and that has good learning properties. But I want to say that in the context of this project, so in the context of the use cases of AI for RealNet, the decentralized training and execution is one direction of investigation, which is interesting, because we, again, need to break the curse of dimensionality of the problem. Okay, so now just some comments on the future research direction of multi-agent problems in general. So one possibility is multimodal communication, in which we have multiple sources of information that are shared among agents. So we need different channels to communicate different sources of information. Then we have model-based algorithms, which are algorithms in which we have a model of the environment, and in single agent problems, they have been proven beneficial in some cases, and they can be extended also to the multi-agent setting. Then we have inverse reinforcement learning that, again, is beneficial for standard single agent problems, where inverse reinforcement learning means to computing the reward function starting from a set of experience collected by expert agents. In this case, it can be also useful to extend to the distributed setting. Then we have safe algorithms, in which we want to impose safety constraints on training and execution, as they can be required by specific application. And then we have the usage of large language models that can be used in different cases. For example, prompting methods to generate actions, or they can be used to provide additional information to agents in the form of textual interactions. Okay, that's it for this part. Now the floor to Marco.
Okay, the second part of this webinar is about hierarchical reinforcement learning. So until now, we have talked about the problem of the course of dimensionality which we face when we consider problem with large state and action spaces. Now we move the focus on the problem of the curse of horizon that we face when we have to make planning over large time horizons. And the two main challenges in this setting are the exploration over large horizon, because we have to plan an effective strategy to explore over a large horizon, and the second challenge we have is the credit assignment problem, because we have to assign the credit to action which occurs far in the past. So the solution that hierarchical reinforcement learning framework propose to these problems are based on the idea of splitting long horizon problem in sequences of short horizon ones which can be handled in a more simple way. In particular, let's consider the problem of going on holiday. The task of going on holiday is a very long task which involves several subtasks. And for example, the high-level goal we want to follow are, for example, booking the tickets, going to the airport, and so on. And every high-level goal has some subtask we have to do. So some low-level action we have to perform that are, for example, for booking the ticket, opening the website to book the ticket, enter the flight information and the date and so on, while, for example, going to the airport require us to go to the taxi stand, call a taxi, and so on. So the idea is to break the complexity of this very long horizon task into a sequence of subtasks we can perform in an easy way. So hierarchical reinforcement learning solve this problem of sequential decision making in long horizon problem by decomposing them in simple subtasks. Here we can observe how in the figure we see that we have a master policy, and the master policy decides which subtask to run in order to perform a given action. So the subtask perform low-level action, and the master policy control the high-level process we are following with our agent. So usually hierarchical reinforcement learning problems are formulated using the semi-Markov decision process framework. In this framework, we have a tuple of elements like in standard MDPs, and in particular, we have the set of states, which is defined as usual for Markov decision process. We have a set of actions that, in this case, are not one-step action, but they are temporally extended action. They are also called subtask or options. And these temporally extended action are action which last for a given number of episodes, which is not predefined in general. And then we have the transition probability, which is the probability of going in a given next state after having played a temporary extended action, and the probability of finish the action in a given time horizon, time step. Then we have the reward function that even this reward function is not defined over a single time step, but it is defined over but it is the accumulated reward over a given time horizon after having performed an extended a temporary extended action. And then we have, as usual, the time horizon in the case of finite time NDPs. So a possible solution to define this temporal extended action is the option framework, and in particular, an option is a set of 3 elements. In this case, we have that the first element is the initialization condition, so the rules and that tells the high-level policy when we can call a given subtask. Then we have the low-level policy by 0 that we follow when we activated the subtask, and last we have our beta 0, which is our termination condition, that is the criteria that we use to decide when we want to stop a given subtask. So each option in this framework will solve a given subtask that can be handcrafted or can be a reinforcement learning problem itself. We will talk later about these 2 possibilities. And as we have defined these two levels in our choice, so the high-level policy and the subtask, also the value function we want to optimize will be composed by 2 parts. In particular, we have the more internal part, the one in orange, which is the part in which we want to maximize the behavior of the high-level policy given a subtask space. And then we have the more external part in which we want to maximize in which we want to find the best subtask space. So here we have 2 different objectives that can be optimized separately or together in a joint way. And in particular, for what concerns the subtask discovery, we have 2 possibilities here. So we can decide if we want to learn the subtask space or if we want to embed the subtask space in our problem in a handcrafted way. And even if this case in which we want to handcraft the subtask space, which can appear as easy. Also in this more simple case, we have several challenges from the algorithmic point of view, from the perspective of the reward propagation, the value function decomposition, and in particular the design of the action space. But in general, the final objective of hierarchical reinforcement learning is to learn how to fully automate this pipeline. So also to learn how to find the optimal subtask. And in the hierarchical reinforcement learning framework, we have 2 main strategies that we can follow in order to learn the best hierarchical policy. We have the feudal hierarchy strategy, in which we have an high-level policy which decides which sub-goal we want to follow, to reach, and any sub-goal corresponds to a given subtask, and we give the choice of a sub-goal to a single worker, and the worker has a universal policy which looks at the state in which we are and take the information about the sub-goal we want to follow and decide which action to perform. The second possibility to learn hierarchical policy in hierarchical reinforcement learning is to use the so-called policy tree approach. In the policy tree approach, we have, as before, a high-level policy which decides which is the sub-goal we want to follow, so our goal, and then at every sub-goal correspond a subroutine which call a subtask, and every subtask has its own policy which is different from the policies from the other the other subtasks. Moreover, we can decide to extend the hierarchical reinforcement learning framework also to the multi-agent case, like for the multi-agent reinforcement learning scenario we've seen so far. And in this case, the idea, as before, is to split multiple subtasks across different agents. And here we have several additional problems compared to the multi-agent reinforcement learning standard case we've seen before, and that are the synchronization over the high-level policy, and the synchronization also of the subtask and how to terminate the subtask across different agents of the multi-agent framework. And then we have the subtask space, which in this case becomes non-stationary due to the effect of the action of the other agents. In general, the challenges of hierarchical reinforcement learning, both from the single agent and the multi-agent point of view, are common in both the framework, that are the learning process, which is divided in 2 or more levels. And so, as we have seen before, we have a problem of the reward propagation and the value function decomposition from the algorithmic point of view, and the state and action space design, which increase the complexity of the problem. Then we have the problem of non-stationarity, as we want to learn the policies in general simultaneously at different levels. So we want to learn both the high-level policy and the subtask together. Then we have the problem of global optimality, as our goal is to split so to break the complexity of the problem, and this operation of try to learn to break the complexity of the problem asks us to introduce some bias in the choice we do, for example, in the subtask space. And so we have a problem that this choice we made in order to break the complexity may introduce some bias in the learning process. And then we have the problem of the definition of the initialization condition and the termination condition, and of course of the sub-goal we want to reach. And last, which is also one of the main lack of hierarchical reinforcement learning, the solution that are currently available does not provide, from the theoretical point of view, significant advantage in adopting hierarchical reinforcement learning. So a more theoretical study of the framework is required in order to understand when this framework is useful and when it is not useful. So to summarize, we have seen how we can model hierarchical reinforcement learning problem, and we have seen how to model it using semi-markov decision process with the auction framework. And we have seen how the 2 main challenges of hierarchical reinforcement learning are the choice of are the problem of learning the optimal high-level policy given a subtask space, and then we have the problem of learning the subtask space if we wanted to learn also this part. Okay, I leave the floor to Alberto for the conclusion.
Okay, so now that we have given a general overview of these 2 frameworks, I would like to conclude with the description of some of the research direction we are exploring, we plan to explore in the context of the AI for RealNet project. For what concerns the the distributed reinforcement learning part, what we are currently working on is on a data-driven way to identify the decomposition of the complex problem into simpler problems that can be assigned for their solution to individual agents. As you have seen, the distributed reinforcement learning approach assumes that there are several agents which are in charge of solving a portion of the problem. We would like to arrive to this decomposition in a fully data-driven way so that we are no longer assuming that this decomposition is given by some expert of the problem. This will, of course, allow us to augment the existing state-of-the-art algorithms for decentralized reinforcement learning with this capability of learning the decomposition from data in either adaptive or non-adaptive way. Instead, for what concerns the hierarchical reinforcement learning part, we are planning to work on the extension of the temporal abstraction approaches, which are currently available in the literature for dealing with simple problems, so problems that are called tabular, that is characterized by having a finite space of the states and action. What we want to do here is to extend those approaches to a very powerful class of reinforcement learning methods that are called policy search, which instead are naturally able to deal with the possibility of having complex, possibly continuous spaces of states and actions. And as a last research direction, which provides a different view of the idea of a hierarchy in reinforcement learning, is what is depicted in this slide on the right part, that is the possibility of designing a hierarchy which is no longer related to the temporal abstraction, but is instead related to a hierarchy of agents, in which we have lower level agents which take decision on a small portion of the system, possibly with a high frequency, and then those agents interact one another, but not directly, but by means of the presence of a manager that is an agent of a higher level, which possibly acts at a smaller frequency and exchanges information among the agents. Of course, this hierarchy can be extended beyond the two levels, having possibly a head manager or even further levels. The challenge here is, of course, the one of minimizing the communication between low-level agents and managers, because communication is costly, but of course it's necessary if we want the agent to achieve a certain degree of coordination and in the end arrive to the final solution of the problem. So that's it from our side. I would like to thank you everybody for your attention. Here is the list of references, and of course we are happy to take any question.